If you remember, I told you that we're gonna start chapter 4.10. In this chapter, we're gonna talk about eccentrically loaded foundations. We have centric and eccentric. I think you remember that when in strength of material we talked about, for example, this member. Um, what was this? You remember that, for example, we called it neutral axis. And in this case, when we apply a moment, a bending, about this axis, everything is what? Symmetry. What does it mean, symmetry? If you remember, for example, one part was under compression, the other part was under tension. How? For example, if I want to show it in 2D view, we have a bending like this, we have a moment, and then this is the distribution of the stresses. What would happen in this case? One part is under compression like this, the other part is under tension. Okay, the stresses are like this. So in this case, for example, the distribution is symmetric. If you remember, we talked about eccentric loading, for example. For example, if I think you all remember that equation. For example, this is origin O and this is force P with a distance of D. What is sigma MO? Sigma MO is equal to D dot P. Yes. And what about sigma Fx and sigma Fy? In this case, for example, assume that this is x-axis and this one is y-axis. Sigma Fx is 0 because there is nothing along sigma x-axis, and sigma y is minus p. Yeah. What about this shape? This is point O, this is force P, and this is bending of M equal to PD. If I write the equations again, what is sigma M O? We have one concentrated moment equal to P dot D with the direction of clockwise. In this case, again, the direction is like this. Clockwise, sorry, if you remember this one, it was negative. And sigma Fx is 0, and sigma Fy is again minus 4. So technically, we assume these cases as two equal cases. So these are equal. You know the difference between this sign and this one is this. Their function is same. However, their shape, their details are different. So we call them two equal cases. Okay. Now, in this case, if you remember, for example, we had a beam once it's For example, under pure bending, subjected to pure bending. What does it mean, pure bending? Pure bending means just bending, no forces. In the other case, we have, in the other case, there is a beam again with same dimensions, but different loadings. In this case, we have a bending plus what? An axial load. In this case, we have a combination of bending and axial force. So this case is pure bending, and this case is the combination of moment for bending M and P. We may have a second case, a third case, like this. Pure load or pure axial load. I'm gonna talk about the stress distribution in each of the three cases. Okay. Now, how can we relate these cases to our foundation design? The first case is like this. We have a foundation, and the column is located at the center of the foundation. Okay, so let me write it in. This is the center, and we have a column like this. The column that's connected to the foundation. Okay. In the second case, we have, so what is this among these three cases? This one is pure, this one is pure axial load. So you can see that all we have is an axial force and no other loadings. Okay, I want to talk about another case that is the topic of this chapter. Suppose that this is our foundation. This one is B, for example, and this one is L. This is the center of B, and this is the center of L. So that would be the center of our foundation. Okay, but instead of being here, the column is somewhere else, like here. So the column is a force like this. What about the other case? The other case, I mean pure bending. You already know about the connections, the supports. What is this? We call it hinge. What is this? Fixed. What was the difference between hinge and fix? In here, all we have is forces, but in this case, we have forces and bending. So if we have in here, if we connect our column, for example, in the center, but with fixed support, our case would be, for example, P and M. Let's forget this case. Let's forget about this case. And let's concentrate on these two cases. Okay, if you remember, I explained it already. We can we can equalize this foundation, or we can simplify this uh, arrangement with a with a simpler arrangement of column and field and foundation. How? Why we can make it easier? Because all we should because we need to find the stress distribution below this foundation. How? For example, because everything is uniform in this case. Everything is uniform. Okay. What does it mean uniform? That means if I want to find the stress distribution in this case, for example, this is the stress distribution. And for example, this is P, and all of them are tension or tensile stresses, and all of them are equal. What is the amount of these stresses? Stress is equal to P divided by M. In this case, what is the amount of stress distribution at each point? If you remember, sigma is equal to mc over I, and distribution is not uniform. In some cases, in some parts, we have larger stresses, like here. In some parts, we have, for example, zero stresses at which location? At neutral axis. So, for each of these cases, we have a different relation, we have a different equation. So, if I want to find the stress distribution below this one, it is obvious the stress distribution because the force is at the center of this foundation, and the stress distribution is uniformly distributed, and the stress is uniformly distributed. What is the stress at each point? The area divided by the force divided by area. That's why, look at here, that's why when we find QU, Q is equal to C and C plus Q and Q plus whatever, QU is area dot QU. So the capital Q is area dot QU. What does it mean? That means this one is Q divided by A because of the uniform distribution. Okay, because of the uniform distribution. But if I ask you to, for example, when we have a bending, when you are in a bending case like this, the stress distribution is like this. In some cases, we have tension. In some cases, in some parts, we have compression. So the left part is under compression, the other part under tension. Any questions so far? Is there any problem? Everything is clear.
Yes.
Okay, so what's gonna happen? Okay, let's get back to this case. Uh, if I want to find the distribution for this case, what's gonna happen? I already know that the distribution in this case is like this. So you can see that it's not uniform. For example, in here we have sigma, all parts are under compression. Here we have sigma 2, here we have sigma 1. It's obvious that uh, this part, because of this pressure or the stress at this part, because of the local pressure of the column, is higher than the stress, compressive stress at the end. I think you can easily feel it. Yes, here, if for example with your finger, let me, uh, for example, this is your case. I'm going to show it with, from top view. E, for example, L. If you apply the force here, it's obvious that the local area or the neighbor the neighbor feels more compressive pressure than, for example, here, like this. Okay, but how can we get this one? As I said, to get this one, it's better to use uh, some simplification. How? I'm gonna split this case into two cases. The first one, pure bending. The other one, pure axial loading. Okay, how with that equation or with that I explained it, yes? This is, for example, E, this is P, and this is O. This is O, the origin or the center. This is E. E stands for eccentricity. And when E is aligned x-axis, for example, this is your x-axis, because in future we'll see that in some cases we have uh, uni eccentricity or eccentricity in one way like this, or eccentricity in two ways. So in some cases you have both ex and ey. Okay, so in here we have ex, and if, for example, eccentricity be in the other place, we have ey. If I want to show you ex and ey from top view, like this, for example, this is the center. If the column, instead of being in center, uh, is located in this case, all we have is one eccentricity. But if the column be in this place, we have two eccentricities. One of them is ex, the other one is ey. Okay, and this is very common. For example, I told you once that suppose when you want to design something, the first option or the first choice is being symmetric. So if you want to design, for example, a building, your first option, your first choice should be, for example, rectangle, circle, like this. But some cases, because you can't guarantee that in all your cases, the ground that you wanna, the property that you wanna design is symmetric. Or, for example, once I told you that in some cases, for example, this is your ground, this is your property, and you want to locate a column in here. You should not, it's not about your choice. In many cases, you should locate the columns at the borders. And in here, this part, the blue part, is not your property. It's your neighbor's property. So you can't continue your foundation to your, you can't extend your foundation to your neighbor's property. So in these cases, you have to locate your foundation like this. Let me see if I can show you. Once I talked about all of them, uh, here. For example, look at here. In this case, the column, for example, in this case, column is in the center, so no eccentricity. But in this case, as I said, because of the neighbor's property, the column is not in the center. And in this case, you have this is your center, and this is your eccentricity, EX, for example. Okay, so when you want to design or when you want to analyze this type of foundation, as I said, it's better to use a simplified method. What is that method? Um, to split it up into two cases. In the first case, you assume that you have only a pure axial loading at the center of the foundation. So this is the center, this is the foundation, and you have a force equal to this one. Exactly, a force with the same magnitude, but in the different location. The location is at the center. Okay, and you all know how to find the distribution. I explain it. The distribution here is what? P divided by area. P divided by area. I'm gonna call this Q sigma C, for example, 0. Okay. For the second case, that is pure bending, we have a foundation with a bending at the center, and let me ask El Shot, what is the first? What is the direction, for example, the bending this by clockwise or counterclockwise? And also, what is the magnitude? This is my shape. This is my first. This is my actual arrangement, and I want to split this into a axial load and a bending. So, what would be the magnitude and the direction of the moment? Elsha, do you hear me? Alrighty, what's your answer?
This is for the pure bending, yeah?
For the pure bending, yeah. I move
Uh,
the force to the center.
uh-huh. Okay. This goes towards the clockwise, and it will be
Uh-huh.
minus.
Clockwise like this, okay? And the magnitude?
Minus.
Magnitude. For example, P dot what?
That P dot X.
Yes. So in this case, we have a moment. Magnitude is P dot EX. And if I put my thumb here, try it. If I put my thumb here like this, uh, and the rest of my fingers will be like this. So uh, my thumb is along this axis, and the rest of my fingers moving or rotating with this direction. So this is my moment, and this is the magnitude is P dot Ex, and the direction is like this. So in this case, how would be the stress distribution? In here we have tension, in here we have compression. So this is my new distribution. I'm sure that you heard about superposition rule. Superposition rule. Normally, what is superposition rule?
You can replace the force with a moment.
No, superposition rule means the final. This is, for example, another distribution. Let me write this. Let me name this, for example, distribution 1, this 1, and this one is this 2, or distribution 2. Okay, superposition rule says that instead of finding the distribution, the real distribution directly, we can split the loads and find each uh, distribution, and finally the final distribution is distribution 1 plus distribution 2. What does it mean? That means if I want to find the distribution at this point, the distribution at this point is, for example, here is sigma T1 and here is sigma C1. At point A, point, for example, B, point C. What is sigma A? Sigma A, I mean the stress at point A, is this one, sigma 0, sigma C0 plus this one, sigma T1. What about B? At point B, the distribution in here is 0. So sigma B is sigma C0 because all of them are uniform and equal, um, plus 0, and sigma C is this one, sigma 0 plus here sigma C1. And you can see that the direction of this stress is upward here and this one is downward. So for example, this one is uh, uh, these ones are negative and this one is positive. Okay, let me give you an example with numbers so you can feel this better. For example, the distribution here, for example, for this case, let me show you from top. This is our column place. The eccentricity, for example, the length is 5 meter, and the eccentricity, and this is 2 meter. The eccentricity is about, for example, 20 centimeter. Okay, and one point, you are not allowed to locate your column in any places that you want. I'll explain in future, but in some cases, when the stress here is 0, you'll see that you have overturning. Okay, I'll explain it now. Okay, it might be a little confusing, but I'm trying to make it easier. Um, this is top view, this is 3D view. Whose 20 centimeter over 2 meter is equal. This is the eccentricity, and this is our column. The force inside the column is 10 ton. Okay, so I'm gonna explain. I'm gonna split it into one axial bending, axial loading. What is the axial loading? One force. And what would be the distribution? Something like this. How much is this? P divided by area. What was area? 10 ton divided by the area is 2.5. Yes, 2.5. Force is 10 ton. So the stress is 1 ton per meter square. Okay, the next case would be pure bending. In the next case, all we have just a moment clockwise, and what is the magnitude? 10 dot point 2. 10 dot point 2. P dot ex, and the answer is 2 tone meter. In here, we have this type of distribution. And this is the distribution in this case. Sigma t, because at this part we have tension, and this part we have compression. Okay. What is sigma t and sigma c? Sigma is equal to mc over I. What is I? This is the axis. The moment m is about this axis. Yes. What is I? 1 over 12 bh over 3. So in here, uh, b is 2, h is 5. Yes, it's like this. If I want to rotate this case and show you, you had this before, h, b, and this was, for example, ix. What was ix? Ix 1 over 12, bh over 3. Okay, I'm gonna just, if you just rotate this case, you get this one. So I is 1 over 12, that's 2.5 over 3. The answer is, let me see,
Answer is 20.8.
20.8, and the dimension is what? Meter 4. Um, and now let's find C. What is C? Who knows? Normally, what's C?
0.2.
What? C
0.2.
0.2. C mc over I. Forget about eccentricity. C is 2.5. Forget that. In this case, for example, we have 5, 2. What was C? The distance between
2.5.
neutral axis and, okay. So sigma is m. What was m? 2. C 2.5 over I 20.8. The answer is 5 divided by 20.8.
0.24.
0.24 ton per cubic meter. Okay, so because everything is symmetric, in here we have 0.24 upward, in here we have 0.24 downward. Okay, so please just take a moment and think about the superposition rule. What would be the superposition rule in this here? So in here it is 1, in here it is 1 ton per meter square, 1 ton per meter square. And if I want to find the total answer, we did it uh, in our strength of material for example, torsion, if you remember. The final answer, the final distribution would be in here. This one is negative, yeah? But this one is positive. What is the stress at this point? Who knows? This point is like this, and the answer is 1 negative or 1 downward minus 1 plus 0.24. What is this here? Minus 1 and minus 24. So in here the answer is minus what? 70.76. Answer here is 1 minus 1.24. What would be the total distribution? Something like this. We can see that distribution is not equal and uniform anymore. Because of what? Because of the eccentricity. So generally, eccentricity is not a good thing, and you should avoid constructing eccentric foundation. But as I said, something you can't avoid constructing eccentric foundation because of special cases such as external or edge, for example, columns. Okay, but when you have eccentric foundations, the distribution is something like this. Do you have any problem? Did you understood? Did you understand this part? I mean the superposition.
Yes, teacher. And one thing you said about the total answer. What's
Yes.
the our answer? The
What?
my what's our
Okay. The
0
answer
point?
is this. If I ask you to find the distribution, if I ask you to find the distribution of this foundation, finally you should tell me that the distribution is something like this. Okay, this is the answer.
Ah,
Okay,
okay.
but you know, you're not gonna use this in your calculations. Okay, another thing. You can see that the pressure here let me show you. Okay. Can you see my fingers now? Yes or no?
Yes.
Okay, suppose
Yes,
that
teacher.
this is our foundation. Let me show it in this. This is our foundation, okay? And when how can I maximize this? Okay, when the foundation is at the center, when the column is in the center, uh, the distribution is uniform. So it moves uniformly down. But when the column is not in the center, instead of being in the center, for example, let me show you a better. Instead of being in the center, suppose that it's, for example, at the edge. What's going to happen? It will rotate. Yes? For example, when, for example, the eccentricity is small, this rotation is not remarkable, like what I showed you. In your case, the eccentricity was just zero point 0.2 or 20 centimeters. But what's going to happen if you put your column, if you locate your column, for example, at a distance or at a large eccentricity? The column or the whole system, the whole foundation will what? Will rotate. We call this overturning. And it's a failure for foundation. Because when the stress at this point, you can see that when I put the column, this is the center line, for example. If I put the column, for example, in the right side of the center line, one side is under compression. For example, this part is under compression, but this part is under tension. If the tensile stress here uh, reaches zero, we'll have overturning, and this is a uh, bad thing in foundation. Understood? Should I explain more? It is obvious. It's obvious. So you can easily assume that you can easily imagine this overturning. Okay, because when everything is centered, everything is uniform. When you put your column out of the center, you would have what? Rotation, overturn. And you should put your, or you should uh, put your column in an area that no overturning happens. So, for example, you are not allowed to put your column like this at the edge because you'll have overturning and it's a failure. Okay. So, how can we find the safe value of this eccentricity? I just told you that. For example, if I increase the amount of eccentricity, for example, at first, this is E1. Let me write this. This is the first case, E1. This is the second case, E2. And this is the third case, for example, E3. As I told you, if we increase the eccentricity, the foundation will rotate. And this is not, let me see if I can show you in your book. Here. You can see that in here, you can see that if you increase the eccentricity E, you can see it here that the foundation rotates like this, and this is a failure. Uh, so, for example, what is the safe value or what is the maximum value, maximum allowable value for E? From the superposition rule, you just saw that in the tension part, total sigma is equal to P over A minus MC over I. When sigma total reaches zero, we call this critical value or critical condition. More than this, is failure, but less than this, it's okay. So how can we find E from this equation? P over A, what is A? That's L, minus, what was M? P dot E, what was C? Remember that? L over 2, for example, or B over 2, divided by I, 1 over 12, B, L3. If this one be 0, E, if you solve this equation, you'll see that E is the maximum value of E is, let me find it, you can hear P over B dot L, and this is 6. So instead of P in your book, Q is used instead of P, and 1 over BL minus 6 divided by BL2 at P should be 0. This one is not 0, so this one is 0. Or let me factor L even. BL. So this one should be 0. So E is equal to L over 6. So in X direction, the Emax is L over 6. In Y direction, Emax is B over 6. Okay, memorize that. If you check your book, you can see it here. When E is less than B over 6, you can see that we have this part, this type of distribution. But when E is more than B over 6, you can see that this part is 0. And this part is already overturned. And we can't open count on this part. But you just, I explained the whole concept to find a whole concept about eccentric foundation. But you just saw that it's a little not complicated, but you need to find many factors. If you check the book, you can here, as I said, we have one-way eccentricity, and in chapter 4.12, you see two-way eccentricity. So, uh, um, in case of one-way eccentricity, the book and other, not this book, other books suggest effective area method. Effective area method. You can see that. Let me find effective area method here. By using this method, you can find your, you can continue your previous calculations. Okay. QU was C and C plus 1 over 2 B gamma and gamma plus factors. Instead of changing this one, you just need to change your E, and you just need to use B prime. This method makes it much more easier than following this process. Okay, so and when you want to find Q, instead of A that QU, you should find effective A or A prime that QU. What was A? B dot L. What is A prime? B prime dot L prime. What is L prime and B prime? Effective dimensions. Effective dimensions. Effective dimensions. How can we get them? Easily, very easy. B prime is B minus 2e. When you have one-way eccentricity, L prime is L. But when you have two-way eccentricity, you should find L prime too. Future, it's a little complicated. Two-way eccentricity, 4.12. Um, like this. You can see that in Kit's case, you have both EB and EL. So finding L prime and B prime is required like this. So as I said, using effective area method is really simple. All you need to do is just find B prime, and the rest of equations and calculations are same as before. And this is your effective area. What is this? 2e, b minus 2e. If you follow effective area method, there is no need to check this one. I told you that you should check if e is less than b over 6 or more than b over 6. But if you follow effective area method, all you need to do is change b with b prime. Any question? I'm gonna solve a couple of examples in next session, so you'll get it better.
Okay, teacher.
Okay, that's enough. Here. No. And showers correct for the heart. Where is the heart? Upstairs. This here. See you next time.
Sir,
See.
But
could you please upload this on the YouTube? We still can download them on Teams.
this class,
Yes, sir.